Okay, I think we can get started.
Right.
Welcome, Loy, to the 6th weekly robotics meetup. And just FYI, as usual, we are recording this meeting. So yeah, the floor is yours. And after the meetup, we'll get to ask some questions, hopefully.
All right, then well, again, welcome everyone. Good evening, at least here it's evening. Welcome, good, whatever, appropriate in your time zone. So my name is Loy van Beek. I'm a team member of TechUnited Eindhoven, of Eindhoven University of Technology in the Netherlands. And since we participate in RoboCup at Home, which I'll must ask me to tell a bit about, and yes, a lot of questions which we'll get to in the end, I hope. But yeah, so first a little bit about me. As I said, I'm Loy van Beek. Since last year, I'm a proud dad, and as long as you do robotics, it's always fun to see how kids learn, etc. So much more dexterous already than anything I could program in that same amount of time. I'm also based in the Netherlands. I work for Motion Robotics, which is a spin-off of Fraunhofer IPA in Stuttgart, which means I've been working remote already a year before the whole pandemic hit. Visited that before then. I visit them roughly once a month. My job there is developing high-level autonomy and manipulation for the robots on the pictures. So on top we have the CareRobot 4, which we've deployed in, for example, in Media Market to guide you to your new TV if you want one, or that kind of stuff. At the moment, we're looking for a perception engineer. So if you're good with PCL, OpenCV, that kind of stuff, send me a message. Before, I worked for Ultimaker, who make 3D printers. Nucleo technology also does some raw stuff. Robot Rose, which was a company that is try to develop a robot for elderly and handicapped care applications. And before I've got my master's in artificial intelligence and got a bachelor's in mechatronics. If you want to follow me on Twitter, my Twitter handle is @loybeek. All right, so I'll be telling a little bit about RoboCup, and specifically RoboCup at Home, and even more specifically about my team, TechUnited Eindhoven. So for starters, what is RoboCup? RoboCup is a relatively large worldwide robotics competition. I'm not sure if it's the largest. I think First Robotics is even larger, but RoboCup is pretty big. This started in 1996, the first World Championship a year later. I think the first one was in Japan, which is where a large part of the community, etc., started. The goal is, or our goal is to beat the human world champions of soccer, of course, in 2050. But of course, also promote artificial intelligence and robotics research. So there's a world championship every year, which has about 2,000 to 3,000 participants with up to 500 teams. The variation is a bit of where it's being held. In 2019, it was in Sydney, which is a bit more expensive to get to for a lot of teams, apparently, than, for example, Germany. So that was a bit smaller. But there are lots of smaller, more regional competitions. For example, my team visits the German Open in Magdeburg, Germany every year. Our soccer team goes to the Portugal Open, but there's many more of these competitions all over the world. RoboCup is comprised of many different leagues. So there's soccer in several variants. There's rescue robots, RoboCup Junior for kids making robots. There's a bit of more industrial applications with, not with industrial robots, but with, I'll talk about that in a bit. Most of these leagues also have a simulation variant, which was, I guess, featured last week in Darko's presentation as well about webbots. Some of the competitions use webbots for their competition. But the most interesting league, of course, RoboCup at Home. So this year RoboCup will be held completely virtual, unfortunately. That's going to be from June 22 to 28. It was last year, it was supposed to be in Bordeaux, but due to Corona, of course, that didn't happen. And as I said, this year, everything will be in simulation and virtual. There's RoboCup has many different leagues. So one of them is soccer leagues, and there's even different variants of of robots playing soccer. So there's a couple of leagues playing soccer while walking with these Now robots, for example, which is quite dynamic. So these, not sure if this video is from last year, but I'm amazed how much faster these robots got over the last couple of years. They are super fast at getting up when they fall over. But there's also different leagues with teams building custom humanoid walking robots of this size, of the Now size, but also what they call teen size, which is well, the size of a 10-year-old kid, for example. So there's much larger robots. Then there is more driving robots that play soccer. So this video clip is also from TechUnited, so our soccer team. They play in the mid-size league. There's also a small-size league which has these more robots a bit larger than a hockey puck, and that play soccer really fast. But these guys are also pretty fast. So let's take a look there. So this clip is from the finals in 2019, I think. And the cool thing about these robots is they have this bell handling mechanism, which means there's two wheels. There's two wheels on the front of the robots, and by controlling them well, the robots can even drive backwards with the ball, which worked so well. They it was put a limit on, because if you just drive backwards with the ball toward the goal, then the keeper can see the ball, of course.
The video is really loud. Can you?
Yeah, sorry.
Okay.
I'll have a commentary there, but so I was saying these robots, you have a ball handling mechanism which they can use to even drive backwards with the robot, with the ball. And there's a solenoid in there that kicks the ball, and they can do this pretty accurately. So our team has been world champion for, I think, 3 or 4 times now. So that's really cool. Right. Nope. Next one. All right. Then there is rescue robots. So these are robots that are supposed to help in disaster-like situations, so where they have to find, for example, people that might be laying around, close what's it called, close valves, all that kind of stuff. Be dexterous and diffuse, pull out a fuse of a bomb, that kind of stuff. These are partly teleoperated, but there's also so they have varying levels of autonomy. I don't know how autonomous this is, but it's pretty fast. So I guess this is autonomous even, but I'm not even sure. Yeah, I wish our robot could do it that fast. For example, oh, by the way, this is quite interesting. I think many of you have heard of the Hector Slam package. That was actually created for this competition. And there's a company called Energy Robotics, which is now a spin-off company by some of the a winning team in this competition. So that's pretty cool. I think by now they are using a spot robots to get around, and they do inspections, that kind of stuff. So so this league actually has a spin-off company, which I think is pretty cool. All right, and next we have RoboCup Junior, which is for kids, of course, and they also do this soccer and rescue leagues, but even smaller. But also RoboCup Onstage, where the kids make robots that do some dance or some act, etc. Also kind of fun. But yeah, it's also really a lot of kids at RoboCup. It's crazy amount as well. Then there is more industrial leagues. So one is at work, where you have these KUKA U-bots robots that drive around picking stuff and putting them on machines. And there's also a logistics league which is more focused on planning with also in a simulated factory kind of setting. I'm not too familiar what exactly is going on in these, to be quite honest, but that's the gist of it. And then, of course, there's RoboCup at Home, which is entirely focused on service robots. So this takes place in a simulated home environment, and just the direct surroundings of that home, but also in a restaurant, which is before the competition heads to that restaurant, is completely unknown to the teams and to the robots. So at the moment, this works with 3 robot types. Originally, they started out with only custom robots, but since I think 2017, there were 2 standardized platforms were introduced to the league. One of which is the Toyota HSR, or human support robot, and the other one is the SoftBank Pepper robots, which is more of a social robot than being able to manipulate, etc. All the rules are defined by a technical committee, which I was part of for a couple of years. And every year at the World Cup, by now, there's about 20, 25 to 30 teams, depending on the location. All right, so these are the types of robots you can expect at a typical RoboCup at Home competition. So I think there's a common theme through all these robots, which is there's a mobile base with essentially a big stick on top, and to the top of the stick there's cameras and an arm attached, which occasionally the arm can move up and down, and the cameras can move up and down. And that's a common theme you see also, for example, in the Hello Robotics' stretch robot, which follows a very similar theme. So how does RoboCup at Home actually work? So there's a whole bunch of challenges, and most of these are the commands to the robots are of course given through just by speech commands. All these different challenges, they are so you do not only get points when you finish the entire challenge, for example. It's not an all or nothing deal, but you get points for different parts of the challenge, of course. And to even out good luck, but also bad luck, we take, if you get 3 attempts at every challenge, we take the best 2 out of 3 attempts. So that way we kind of reward robots that behave well consistently. But if you have bad luck, that's okay. But if you have only one shot where you are lucky and something worked really, really well, or something else happened where you got lucky, well, that you need to have at least 2 of those runs, or otherwise it still rounds out. Before the actual challenges start, there's about 2 setup days where you can learn the environment, make a map through SLAM, for example, or train your perception. Since there's a new set of objects every year, which are local objects. So if you're, well, for example, some groceries. So when we went to Japan a couple of years ago, well, there's Japanese groceries, which are certainly in some way distinct, a little bit different from for example, European groceries, which makes for an interesting learning problem as well, and also incentivizes you to have a good perception training pipeline. It's really fast as well. So the challenges are split up in 2 stages, each with about 4 or 5 challenges, and the top half goes to the second stage as well. And then there's some finals. So what kind of challenges are there? What do these robots actually do? Well, what you see pictured there is storing groceries. So the robot finds a big table with lots of groceries arranged on them. And the robot's job is simply to pick up all those objects and put them in the right spot in a pantry. And then, for example, drinks go with drinks, apples go with apples, other fruits with other fruits, etc., etc. Then there's another challenge, which tidying up. So cleaning up objects that don't belong, or put them in the right place, or throw them in the trash, that kind of stuff. Another one is carry my luggage, which takes place partly outside of the apartment or the arena. So the robot has to follow a person, go to a car, carry a bag, for example, from the car, bring it back to inside of the arena while avoiding people, etc. But also guide back outside someone else to help carry more groceries, that kind of stuff. Sometimes a bit of contrived scenarios to make things interesting or test things we want to test. One thing also to deal with there is, for example, 3D obstacles. So when the robot comes back in, something has changed. So maybe there's a table there or which looks like you can drive underneath it if you just use your LiDAR, for example, on the ground level. But well, you don't want to drive into the table surface as well. So you have some 3D obstacle avoidance, etc. Another challenge is receptionist, as someone already mentioned. And the purpose there is to introduce new guests that are arriving to the front door. The robot goes to the front door, sees, hey, there's a new guest, gets their name and introduces them to the old guests that might already be there and find them a seat. So check where is there a place to sit, etc. And then remember where all the people are. Maybe they moved around and say, oh, this is the new guest, his name is blah. Hello, these are the other guests, that kind of stuff. I think the most interesting challenge we have is the general purpose service robots, in which the robot has to perform a large a task composed through a very large grammar. So the command is actually spoken to the robot. For example, bring me a drink from the kitchen, or go to the hallway and answer a question. Tell me the time, tell a joke, that kind of stuff. So this deals with natural language understanding, a bit of task planning, sometimes even dealing with wrong info. For example, that an object that the robot is commanded to get is not actually there. So the robot has to find another way to achieve the task, or report back what's going on, why it cannot perform the task, or if you are asking for a drink, maybe suggest another drink, that kind of stuff. So as I said, the best half of robots go to stage 2, where there's more difficult challenges. For example, is cleaning a table, which involves putting dishes away, so grasping more difficult objects. There's also this restaurant challenge. So we take all the robots to a restaurant type environment that is somewhere in the vicinity of where the competition is held. Sometimes that's inside the venue, but sometimes it's even been to an actual restaurant outside of the venue, out on the street, for example. And then the robots have to, well, this is a new environment for the robots and for the teams as well. And the robot just can map the environment or not, but well, people are sitting there around on tables. They wave at the robots. Robot has to spot that someone is waving, go there, take their order, go back to the kitchen, collect the order, which is being made by someone else still, unfortunately, and then take that order to those people that have been waving, for example. And this also means involving dealing with relatively noisy environments. Last year, we didn't do so well because this was inside the venue, and this restaurant happened to be next to one of the soccer areas. And while we were running this challenge, some guy was calibrating something with a whistle, which was very, very, very annoying. Okay, next challenge is what is that? So that means involves a bit more world modeling, but also gesture recognition. So there's a person in there that just points at an object, and the robot has to go to the object, point at it, and say what it is. So this requires quite some accuracy. And then even more interesting than just GPSR is the extended duration version of that, which simply means a robot or two robots are concurrently in the arena waiting for a task for over an hour or up to an hour. And they just get several tasks going on. And sometimes two robots are even running in concurrently, which adds even more dynamic, bit more dynamic stuff to the mix as well. So after this and the top 3 robots then go to the finals, which is scored by an expert jury, but also a group of laymen, which judge for different criteria. So, and that is finals. Always really cool demonstration seat. This is really some really cool stuff typically pops up there. All right. So then a bit more specifically about my team, TechUnited. We've been around since roughly 2011. I've also been involved since end of 2011. So end of this year, there will be 10 years, which is crazy if I think back about this. In 2019, we were world champions, but before we've been asymptotically creeping up there for since 2011. I think first time we participated, we were in 14th place, and then 7th, and 4th, 3rd, etc. Keep creeping up there for quite a while. Our team is part of the mechanical engineering department of TU Eindhoven in the Netherlands, and at the moment we have about 15 members. I think our team works a bit differently than other teams. So with us, this is mostly a hobby. If you do your master's project or graduation project, well, you focus on that. And if you can integrate this into RoboCup, then that's okay, but it's not even required. And it's also not the case. Like, I think what happens in many other teams that there's a group of people dedicated to this project for a year, for example. That's not the case with us. Would be nice, but at the moment we don't do that. And as this being a hobby, so we're not only master students or bachelor students, but I've graduated a couple of years ago already, so 7 years, I guess. Yeah. And there's a couple of other people who already graduated, are working in industry, but are still doing this as a hobby. So we have lots of knowledge carryover to these new members, and I think that is part of the strength of our team. So as I mentioned, we have a sister team with soccer robots. There are about 20 people, and together we do lots of outreach and demos and promotion for technology and studying technology at various schools. At the moment, we are participating with a Toyota HSR robot, but before we had our own custom-built robots, AMIGO. And this whole thing got started as part of the Robo-Earth project together with ETH Zurich, among others. Right, so this is our team. Not the whole team. We cannot take everyone to all these competitions, unfortunately. Would have been nice. Yep. Right, and these are the other team members. So we have Hero, which is this Toyota HSR robots, AMIGO and SERGIO. And the other robots, for example, the Pepper and the Now, those are also great for outreach. People love those. We also have a Player robot, which is even more popular with smaller kids, but not as good for RoboCup. So this is was our main robots that we originally got started with. So this is called AMIGO, custom built in 2011. Price, it's on, I don't know the exact price, but at the moment it's on the insurance list for about 120,000 euros. But yeah, it's as custom built. It's equipped with, it's round, it has a round base and equipped with omni wheels and it being round makes it much easier for navigation, of course. It has two 7-degree of freedom arms built by Philips. There's only 4 of those arms in the world, and half of them are on a robot. It's equipped with 2 laser rangefinders, so one at near the ground level and one on the torso, which moves up and down. On top, there's of course a Kinect camera with a LED bar underneath for lighting. The torso is height adjustable linearly and really handy. I think a lot more robots could use is these robots have just hot swappable cordless drill batteries. So many other robots need to recharge. No need for that with us. You can just hot swap them. At some point they were exchangeable with the soccer robots, not anymore, and that has caused trouble. So do need to watch out with that. If you want, you can get all the designs at roboticopenplatform.org. And another feature for this robot, by the way, is the RGB lights in this more translucent area in its skirts, and that's really handy for getting some basic status info. So if it's yellow, for example, it's on e-stop, and if it's blue, it's driving around. There's a directional microphone on the head, which is really handy if you want to do a speech recognition. But we can also, there's also one of those matrix creator boards. You would have to Google those, but those can do, for example, sound source localization. So if you stand next to robots, that mode is enabled, then you can, then it will look at you and get a much better microphone signal. Let's get out of the light. Then we have SERGIO, which is also a custom built robot much later. Doesn't have its Omni wheels, but Mechanism wheels on a suspension, so it's super smooth when it drives. It's if you do this right, it's barely here. You can barely hear it coming on. At the moment, it doesn't have any arms, unfortunately. Those should be coming. It has also two laser rangefinders, also one in the base and one in the torso. Yeah, also connect just as AMIGO. The height, it can also has a height adjustable mechanism, but it's more of a scissoring mechanism, so it's bit more humanoid looking. Same battery system. Yeah, for the rest, it's relatively the same as AMIGO. And then our current robots. So this is a Toyota HSR robot. It's a diff drive robot, has much less degrees of freedom. But really handy is that it has a camera in the palm of its hand. And one really clever feature that Toyota put in is the suction cup on the finger. So that's really handy if you want to, for example, pick up a piece of paper from the ground. Has only one laser rangefinder also mounted on the base. Stereo camera, RGBD camera, also height adjustable torso. That's unfortunately that is coupled with the arm. So if you double coupled to the arm, so if the torso moves up 5 centimeters, the shoulder of the arm goes up 10. Can cause some trouble. It's sometimes hard to deal with. Very handy thing is the LCD screen in its above it, the 2 eyes, and under the RGBD camera. And finally, this robot being a Toyota, it has the same power button as a Toyota Prius, apparently. All right. And the cool thing about these 3 robots is that they share the same software stack for as much as we can, at least for applications. So we use the same application state machines for all 3 of those robots, and that is based on the ROS SMAG library. Over the years, we've built a large library of sub-behaviors that we can compose applications with. And the way this works is we parameterize all these states with a subclass of a robot object. So we have one of those classes for every robot. So we have an AMIGO class, we have a SERGIO class, and a Hero class. Those are composed of different arms, etc., head, etc., etc. And that allows to wrap around the peculiarities of that specific robot. And one really handy thing is that, of course, you get this if you have a Python console, you can directly control the robot that way without going through ROS topic pub, etc., etc. And the cool thing about being able to swap these robots around and using the same application state machine is, of course, that we can pretty easily swap them. In one case, we had a robot break just before a RoboCup challenge. Well, that's fine. We could just in a minute swap out to a different robot and still perform the challenge. That was really cool. And our software is centered around a 3D world model, which is really handy because it allows you to more reason about the world, which is really handy, of course, in some of our applications. And it's much handier to reason about than having separate perception inputs, for example. Right. So what do we do? A software stack. As I said, we have our behaviors are defined with using ROS. ROS to SMAC. For navigation, we use move base, motion planning, we move it, etc. For speech recognition, we use Dragonfly, fortunately in a Windows virtual machine. OpenPose is a part of our stack. OpenFace. To no surprise, we're using a retrained computer vision model, Inception v3. We have some handy logging tools. The SWRI console is really handy. So as I said, we have a world model. Custom build is called add or environment descriptor. And for control, our custom built robots use oracles. And for the HSR, Toyota has built something for us. So the big architecture diagram, as I said, it's centered around this 3D model in the center. Wrapping on top of that, we have these robot skills, which are this Python layer on top of that. On top of that, we have state machines and a whole bunch of different applications that can use that. And of course, we can simulate the whole thing with the same interfaces, which I guess is a good and common practice. All right. So what happens if between control inputs for an application, we have different challenges, but also an action server, which I'll show a bit more in the end, which does planning and a bit of planning and running the composed state machines. That all uses our robot spec state, which is this state library. The console that I also just described that goes to robot skills, and those robot skills wrap the various more common ROS stuff, for example, move base and move it, etc. Then it goes to ROS control. One really cool thing that we have using this action server is a more natural, if you will, language interface. Not entirely natural, of course, but using a close enough to natural grammar. This uses a context-free grammar to parse a subset of English, as you can call this. So, for example, you can and one way we use this is through Telegram, which is an alternative to WhatsApp for those who don't know. One handy thing is this HMI that we use, which I'll also show in more detail next, which we can use to send questions to different channels. That goes through a conversation engine, which tries to gather if we give it an action, for example, an action, but some parameter of the action is missing, the conversation engine converses with the user to finally get all that information, keeps track of the state there. So there's a grammar parser, which is essentially just a context-free grammar parser. And then out comes an action description, which then gets used by this action server to plan the action roughly, and then compose and run the state machine that implements the given command. So this HMI is quite handy. Our applications, they can specify, can call a ROS query action. And the goal there is, the action goal is a description and a a context-free grammar. And this HMI then can use different clients or different servers to ask the same question to the user. So one of those channels can be Telegram, so you get a message on your phone. One can be actually saying something to text-to-speech and then using speech recognition to get the answer. Another way is to simply get an answer through the console if you want to test something. But also for testing, you can replay an earlier conversation, for example, or give a random answer to test what will happen, etc., etc. And this HMI will then just take the first answer that it gets, whatever the answer is, continue the application. Which is, this framework is pretty handy for multimodal interaction with the user. Another server is a GUI, for example, etc. One handy thing is with Telegram is, for example, that you can have custom keyboards. So in this way, you can compose your command like this. And the cool thing with this grammar is that if you have a fixed grammar instead of full natural language, that you can have much easier completions. So according to our grammar, this sentence, I would like can be completed with, for example, apple or a beer or a biscuit, etc. Which makes for a really handy user interface, much handier in some cases than actual speech interaction, especially in noisy environments, but also, well, with speech, it's hard to discover what commands are available. With text, if you get a prompt or a tab completion, you might actually, it's much easier to know what commands the robot can actually take. All right. One cool thing with our system is that it uses this 3D world model called ED. And we use this for, well, as I said, it's the center of our software architecture, and we use this for all sorts of different things. One key thing is, of course, navigation. So we have all these objects, as you can see in the image there, and we just down project all that to the world, to a cost map, and not drive into a table, for example. We also use it for localization. So that when the camera, for example, the 3D camera sees that, for example, that table moved, we can use that to also update the localization map, so that we see the table legs moved, even though, so we can update this map to have a much more accurate model. This creates a bit of a loop, of course, between things, but with some tuning, that's works quite well. Well, as we have a 3D world model, 3D objects, we can also use this for Move It to have a 3D collision world, which Move It can plan in, of course. It's also really handy for perception, because if you render the depth image, the expected depth image of the world model, you can take the difference between what you actually expect, and if that difference is large enough over a region, you can extract a 3D, you can extract a mask for this, which you can use for segmentation and then do object recognition with that. One other handy thing is, it's not sure how well you can see this, are these region of interest, these translucent boxes that are floating around. And these region of interest allow us to filter objects that are, for example, on top of the table, which is defined as a region of interest. As you saw, it's also really handy for filtering out objects or percepts. For example, these walls are really low, which lower than they would be in a actual home environment. So, for example, if your depth accuracy isn't that accurate, and there's, for example, the robot can see someone on the other side of the wall, which is not really possible with high walls, of course. We can actually filter that out and then say, have a query, for example, say, give me a list of all the entities that are in this room. and not just which are all the humans that I can see, but which are all the humans in this room. Right, so this 3D world model is also really handy for adding all sorts of attributes to objects. For example, for people, we can add the skeleton, which we detect through OpenPose. We try to estimate age. The age you see in the picture there for me is not really accurate. I'm not 40 years old, and I certainly wasn't when this picture was taken. But another feature that's being estimated is, for example, shirt color, the gender. It tries to estimate with some neural nets. What type of pose? So, for example, is there a person waving, which is handy in that restaurant application? And all of this together allows for some really handy features to query this world model. So, for example, we can query the world model like, give me all the entities or objects of a certain type on top of this and this entity. Tell me how many sitting people there are. Find the male with the red shirt in this room, what object, how is that person pointing? Which direction is that? Where is his finger? Where is his head? Draw a line through that, and find which object that line roughly intersects with. And our applications, they use not just the ID of the object, but rather an object description, which are then resolved through this world model at runtime. And this is what we call so-called designators, by lack of a better name. So what are those? If you've used SMAC maybe before, it uses something called user data to pass around data between states. So, but if you have started to develop larger and larger state machines, we've experienced that this becomes quite cumbersome to use. It makes it really confusing. So I started to develop something to come around that, and also to use this world model. A previous version of this world model was called Wire, and you could query that using Prolog. Prolog is a logic programming language, so with logical relations between facts, etc. And we could query this to use Prolog to create a world model and define relations, etc. This also got quite unmaintainable because the logic to deal with that was getting duplicated all around slightly differently, etc., etc. So one handy thing was to gather that logic and the query into different classes and objects, and pass that way to get an answer, wrap that in an object and pass that to state machines. And we can do this, for example, for those entities, but also for arms, strings, etc. It's not perfect, but it tends to work quite okay. So one way we use this is specify which arm to use for a certain action, which is quite handy if you have robots with 1 or 2 arms. So we can, if your robot has 2 arms, you can maybe use the other and grasp 2 objects until you run out of unoccupied arms, for example. And we can specify objects, say, or a pose. Say, okay, give me an empty spot where to place something. I want to place something on another entity, use that arm and place somewhere on top of that object. And how that empty spot is then calculated, yeah, that's up to the designator to implement. You can call a service, it can do it itself. It doesn't really matter. And the state also doesn't have to think about that. It just gets a pose stamped and tries to work from there. So it encapsulates a bit of the process. So as I said, the world model for navigation, so it's waypoints in there, but also the outline of an object, which can get updated, etc. So let's see that in action for a bit. No sound, that's off. So for example, one command is inspect the dinner table, and you should see the table moving around. It was updated as the robot saw it, and let's see that again. So the robot drives to the table, inspects it, and then the table, as you can see in the image, the table is not perfectly aligned with the rest of the wall, although it is in the current world model. Robots inspects it, and then it updates it. And you can also see this, the outline, of course, also updates. Oh, well, let's quickly see that. So the object is now updated with the outline, etc. as well. And it also sees, hey, there's actually an object on top of that. It's classified, it gets an ID, etc., etc. One really cool thing about this world model is that we have a user interface to fill it with if we want to. If we go to a new environment or for a demo, for example, this is really handy. So it runs on an iPad. This is a web interface running on an iPad, and as you can see, it's really nice to use. This is really, really handy at demos. So you get a live view, you can control the robots and drag in objects that will pop into the world model. And then you see the resulting world model, etc. So yeah, objects are plopped into the world model with their regions of interest, etc. We also have a button, for example, to extract all the walls and all the, well, it inserts a 3D model of all the walls, etc. One really handy feature is constraint-based navigation goals. So by default, move base, for example, and most other navigation plans that I know of use a pose as a goal. So you can go to this XY position and orientation, of course. We extended this to have constraint-based goals. So you can specify essentially an area to go to, and not just a region or go to within some distance of a point, but go to well, an intersection between objects. So for example, go to a room and then the whole room will get all these pink areas that are the goal, but also go to within some range of an object, like you see on the right there. Go to in front of the table, for example, or you can combine them. So go somewhere near the object inside this room, so that when, for example, this Coke bottle is at the edge of the other edge of the table near the wall, that this goal area does not stretch into the other room, for example. So then, because then the robot would go to the other room if that was closer, for example. That's a really handy feature for a lot of applications too. It's a bit old. The code is kind of old, but based on an old fork of move base. So upgrading that to, say, for example, move base flex or navigation 2, even for us too, would be a nice project sometime. But as it happens, lots of things are nice sometimes. So again, this natural language interface, which I like to show a bit of. So this is again Telegram. Let's make this full screen. So the command we're typing is place a Coke on the dinner table. This is not complete because the robot doesn't know where it is. So it asks, I do not have enough information to perform the task. Where would you like me to pick that up? Answer is cabinet. So this is the conversation engine in work through Telegram. So cabinets. And then robot springs into action, goes to the cabinet, uses the world model and segmentation to find that object, goes there. This was a bit slow. She just sped up 3 times, and I still think can be faster, even though it's sped up. That has improved recently, but it's still not as fast as I'd like it. And then we go to find an empty spot to actually place this object on. Right. So we do, as I said, we do lots of outreach and lots of demos. Some of them the robot has to look a bit ridiculous. This was a robot in traditional Dutch clothing, which looks absolutely horrendous. But it was for a cool demo. We did a demo for Chancellor Angela Merkel. It was pretty cool. So we get to meet some, well, has some friends in high places, I can say. So, for example, R2D2 has a princess, but we can one-up even R2D2 because we once did a demo for our Queen Maxima of the Netherlands, which was also pretty cool. Weird thing is, if you do these kind of demos, there's dogs coming to sniff your robot for bombs, that kind of stuff. So interesting experience there. Cool thing about this demo for Queen Maxima, for example, was that's where that feature with the the constraint-based navigation came from. When we were doing that demo, we were supposed to bring her a drink, and the robot was going to, well, to its goal, where it was to deliver the goal. But guess who's standing there? Our queen, standing in the way. Super annoying, of course. So our robot failed, couldn't get there. So we had to press a button to go to the next step and hand her that drink. And so in the end, it worked out quite okay. But that was an interesting experience. But of course, in the end, our outreach is much more important for kids, for example. So we do lots of demos for high schools, elementary schools, etc. And on the top right, you can see there's so many people coming for RoboCup. Look at a soccer match with robots. When RoboCup was in Eindhoven in 2013, like 5,000 people watching a match of robots playing soccer. That was really amazing. So yeah, lots of really cool stuff we do with our robots, I think. And with that, I would really like to thank you for your attention. And well, of course, if there's questions, please ask.
Yeah, thanks for reminding us. There was a time where you could host 5,000 people in one place.
Yeah, that's yeah.
Okay,
it was a long time ago. Hope we can do that soon again.
Yeah, I will unmute, so allow everyone to unmute themselves. So we have the time to ask the questions now. So feel free to do that. And I'm keep thing recording because I think it's interesting for others who watch it to hear the questions and the answers. But if you don't want your voice to be heard or anything, then feel free to type in the question in the chat and I will read it. Okay, I can probably start because I have some questions. Did you consider checking out behavior trees instead of Smash?
Yes, we have a couple of years ago. But already by then we had a huge library of these state machines already. So the converting would be, well, would take a real lot of time. And also a lot of our team is from mechanical engineering, not all that used to programming in some cases. They get more experience over time, obviously. But also, me as well, I've found state machines to be much more understandable and debuggable than behavior trees. Also for work with Mojin, we've looked into behavior trees, but also decided to stick with state machines, etc. So we did switch from SMAC to FlexBE, but it's still the same. Yes, still the same paradigm, still state machines. But even for planning, so automated planning, for example, there's now Plan Sys2 or ROS-Plan. Those work with behavior trees, as far as I know. So it does get more interesting to look into that as well. I think it's an interesting concept for sure.
For me personally, the biggest value was that I didn't have to refactor the the edge cases where when you have the
Yeah.
switch from one state to the other, and instead you have just one XML and everything results from this XML.
Yeah, one advantage is with behavior trees, as far as I know, is that you can be much more reactive. So for example, if you're busy doing something, but your battery goes below a certain level, it's much easier to respond to that kind of environment, to that kind of changes than with a state machine. For RoboCup, at least most of our applications are guided by this rulebook, which doesn't intend to dictate a specific script to be followed. It doesn't dictate that, but implementing this to a state machine is typically the easiest for us, at least. And it doesn't always require that much reactiveness in lots of cases. We know when to look for this waving person, for example. That should change in RoboCup to have these more reflective or reactive behaviors, but not the case yet. No.
So
okay, go ahead.
Yeah, you can go ahead, no problem.
Okay, so my question, I have a couple of them, but how does the environment descriptor work, like in terms of database? Are you using any stuff like ontologies, or are you just using some database with?
At the moment, this is just an internal data structure. We can serialize it, but that's about it. So our previous version of this world model called Wire was more point-based, so didn't have 3D objects, but just objects were just points in a 3D space, which you could query through Prolog. And that was part of that was developed as part of this Robo-Earth project, which also and that project also involved, for example, NoRob, which is an ontology for robotics.
Yes.
That integration was there, but it's not in this new 3D world model, unfortunately. It's always been on my mind to integrate this at some point, so that, for example, we could query this through RDF or Sparkle or that kind of stuff. That would be really cool. But as many things, we haven't gotten around to that, especially.
I'm asking this because I'm actually doing my master thesis on this now, so right. I'm still looking for what kind of representation do we need. So that's basically the theme of my master thesis. Yeah.
Right.
That's why I was asking.
Yeah. Yeah. So I think this NoRob thing is pretty cool. Yeah, and it would be nice to develop some sort of interface for that. So this add thing is it's plugin based. So there's sensor integration, that's a plugin. The navigation is a plugin, move it is a plugin, all that kind of stuff. So it should be possible pretty easily to write a plugin that offers this interface. And yeah, who knows, that would be really cool. And then you can, so one cool thing we had with the previous world model with Prolog was that we could specify relations, such as, so we had for every challenge and for every environment, we had this separate knowledge base to say, okay, where does type, for example, Coke can, where does it need to be cleaned up? Well, Coke cans, if they are empty, they need to be cleaned up to trash bins. And then we had another entity in a world model, which is labeled as type, which had as one attribute was the type is a trash bin. And then when the robot recognizes an object, say, okay, this robot, this object ID 123 also has the label Coke can, and then we could make a Prolog query saying, okay, where does object of this object of type of class X, where does that need to be? Give me the poses where we can find something where we can clean this thing up and then select the closest trash bin, for example. That kind of stuff.
So in that case, you were not using ontologies for this.
No,
it was just the knowledge base.
Much simpler. Yes, much. Yeah,
okay.
Exactly.
Okay. How do you deal with object anchoring? Like if you have multiple objects of the same category, like same chair, if you have multiple chairs, how do you handle with that?
So especially our previous world model was particularly good at this. So it used a multiple hypothesis tree, if I have the correct name for that. So it tried to, I can send you a link afterwards if you want, or just ask me. But how that roughly worked is, so we have, you have a known state of the world, and you update it, and now you see the object, an object in a different place. So there's a couple of things that could have happened. So if, for example, if you, one demo we had with that was playing this ball game where you have 3 cups with a ball underneath them and you have to follow the ball around. A robot could do that at some point. And it did this by just tracking, of course, just comma filtering, that kind of stuff. But also if an object gets occluded and then you see it again, maybe in a different place, then there's a couple of things that could have happened. It's a new object, that the old object moved there, or is there any other case? Well, so it tried to maintain a tree of all those hypotheses and then just only prune the unlikely ones out. And that's how we try to keep track of objects. So our new 3D world model is much less sophisticated in that regard, but it has many other benefits. So it would be nice to merge the two, and some efforts have been made, but since the guy finished his PhD, that didn't really materialize.
Okay. So my final question, and I don't want to take opportunity from other people. How do you deal with in terms of the execution? So you do the offline planning, right? And then in the execution part, how do you deal with uncertainty and partial observability? Like, do you use any kind of POMDPs, or do you just replan, or?
Yeah, typically we replan. So when our state machine fails, so most work in these state machines goes to reliably retrying and catching all the exceptions that can happen, or edge case and that kind of stuff. So that is certainly not ideal, but it is really debuggable.
Yeah.
So so fair in that case, relatively simple, and that's why these state machines blow up pretty quickly as well.
Yes.
But and we cannot catch everything, of course, and doing some planning, for example, would be much nicer.
Yeah.
But yeah.
Yeah. By the way, Mateusz, there is this new paper from from the DARPA Subterranean Challenge, the team of JPL and NASA JPL and MIT. It's called Nebula, and they describe their approach for the Subterranean Challenge, and they are using POMDPs for this kind of execution monitoring, let's say. I didn't.
Thanks for mentioning.
Yeah. Maybe it can be in the next weekly robotics newsletter. Okay. Thank you.
Yeah. I see one question coming in through the chat, so let's try to answer that before I forget. Mechatronics professor, very interesting achievements.
So maybe
Thanks.
I'll read it. So it's if anyone is watching, he can see it. So it's a question from Carlos. Hi, I'm a mechatronics professor. Very interesting, and congratulations for all your achievements. What would be your advice for undergrad students, newcomers to robotics, that after watching your presentation could feel lost where to begin regarding at-home category?
Geez, that's a tough question, really, because I think RoboCup at Home is really interesting, but also really difficult. And that's also why it's interesting. So where to begin? Jeez. There should be a good answer for this. Yes, start small, I think. So these robots, these challenges, they cover a whole lot of different things. Just pick something and try to solve it. Try to solve that. And there really is a lot of stuff out there. A lot of open source stuff. I didn't mention it, but all of RoboCup stuff is supposed to be open source. So even during RoboCup competitions, we at TechUnited, we pushed, if we have a decent internet connection, which is not always the case, by the way, we try to push it. We push to GitHub during the competitions as well. So even if competing teams can even see what we're trying to do for the finals, for example. So everything is open source. So definitely take a look there. And things have gotten much more mature during my involvement in RoboCup at Home. So for example, when we started, we were not using MoveIt, but trying to figure that out ourselves. Don't do that. Start with, for example, using MoveIt, MoveBase, all that kind of stuff is out there. And if you can avoid it, do not try to develop your own hardware. It's really cool, but super time consuming, and it gives you a lot of control, but you also need to exert that control and fix your robot if it breaks, for example. In return, you get stuff, you sometimes get problems you cannot fix. That's the downside. We have some troubles, of course, with our HSR robots, but it's much more stable for use than our AMIGO robots. So try to use commercial hardware, I think, that integrates well. And yeah, as I said, one success factor of our team is knowledge carryover from more experienced team members to new ones. So it's not a completely new team that has to start from scratch every year, but it's really been developed over the last 10 years. That's hard. So we're not newcomers anymore. So not the best of advice, maybe. But yeah. Definitely start small. Get your navigation to work well. Then maybe add a gripper. Yeah. Hard question. I'll think about this more.
How did you organize the teams? Did you organize them kind of by, or like, did you do like kind of per task or more like per component, or how did you do that? Or was like everyone just doing everything?
Well, there's definitely specialization within the team. So lots of people, I think about half of the people really doesn't like state machines, for example. So they focus on the world modeling, this open pose integration, for example, control, navigation plugins, that kind of stuff. And then the other half of the team roughly focuses on these state machines. And of course there's mixing of those two things. But for example, one challenge was where we had to get this pointing at, figure out where the robot is pointing at. So if we define an interface, say, okay, how can we integrate this so someone can work on that algorithm to find out where someone is pointing, and someone else starts to integrate on that challenge. Yeah, it's quite dynamic how tasks are being distributed, but certain people certainly have their specialties.
Can I make a contribution from my team perspective?
Yeah, sure.
Okay, so in our team, it's a bit like you said, we have division between the team. So different members are responsible for different things. So we have someone, in my case, I'm responsible for the perception. Other person is for the grasping, other for localization and navigation, other for NLP and human machine interface. So that's the thing. Other thing is we make a big effort to document everything. So we on our code we create like tutorials, and we spend some effort to try to maintain the code base so that newcomers are more easily introduced. And then finally, now with containerization, we are starting only now to put everything in Dockers, and I think it's also a push that this virtual competition this year will also make, is that we had planned for almost 2 years, even before I was in the team, to start to make everything in Dockers, but now we really have to make it so.
yeah, it's a good help in that. Yeah,
that's
yeah, good advice there. One thing I also wanted to say to Carlos, where to begin is, I think, is having a robust base layer. So having your robots robust and not fail all too often, to say you can rely on your hardware. That's also crucial.
Okay.
Yeah, go ahead.
Hi, Loy. This is Jaswant, and thanks for the nice presentation. And your team has been doing really nice, and I've already been using lots of resources from your GitHub. Like I've already used ED and stuff like that, but now I'm completely in a new team. So we are like we're not using that, because like our complex software architecture is now different. Like for example, now we are in this team, I'm using move-based plex and stuff like that, which doesn't support, unfortunately, your project. So really looking forward when your libraries get compatible with the latest stacks. But I have a list of questions, but first I will ask only 2 and then give other chance, so that the things don't go wrong. So my main question is, which planner do you suggest? For example, there are multiple local planners available open sourcely. So you have been leading the RoboCup team, and you also have been working at Mojin. So I have been in contact with Mojin for in the last year. I have contacted Hannes Bester, if you know. For a position, it was an unsolicited application, not like a specific for a position, but yeah. But I couldn't make it. I didn't receive any positive feedback from that, but it's fine, not a worry. But as you have been been also on like the production side and also kind of on the research side, so which planner do you think and why it should be used, especially in indoor plannings?
Oh geez, that is really specific. I'm not even sure which planner we use on our with TechUnited. I'm not even sure. That's all nicely abstracted away from the state machines I make.
Okay.
But for with Mojin, at least, we use some stuff made by Fraunhofer IPA that we licensed from them. So there's actually a new company that's spun out of Fraunhofer IPA last year called Node Robotics, and we use their local planner. But it's essentially a time-elastic band local planner. So the closest thing open source is the DEP local planner, and that works pretty well. I think we wrote our own local planner, but I'm not even sure. I would have to take a look there.
Okay, but
the fact that I don't know means that it works quite well, I guess.
Okay, but just another question, like what are you responsible for in Mojin?
For Mojin, I also work on the high-level applications, so building state machines, but also at the moment we're building a new mobile manipulator robot. So lots of dealing with move it and manipulation and all that kind of stuff.
Okay. Yeah. And one more short question is, which simulation would you prefer? Like there are robotic simulation, which is the best and why, according to you?
We don't use simulation all that often with TechUnited, also not at the moment, not at Mojin as well. At Mojin, our simulator is Gazebo, but mostly because it's the default with ROS, I guess. With TechUnited, we were using Gazebo, but some guy wrote our own simulator, which is fairly bare bones, but it's really fast, and hence it's called the fast simulator. But it doesn't do any physics simulation. For example, we just assume that if the robot commands to drive forward, it actually drives forward. So we can actually test our state machines in much more detail, and test their logic and scenario, rather than if the robot closes a gripper, then that something actually sticks to it. And also at Mojin, I've been developing a test framework called Scenario Test Tools, which you can find also online, where you can, instead of implementing a whole simulator or Gazebo, a physics simulator, you can just emulate all the interfaces that your state machine talks to. So, for example, if you call a classifier, instead of actually taking an image through in Gazebo and running your perception on there, it just returns something interesting, so that you can test your state machine in much more depth, and also all sorts of weird corners of your state machine. So that's what I developed for Mojin, but it's open source, and we could use it for TechUnited as well, but we are not at the moment yet. I skimmed through last week's presentation about webbots, but we're not using it, but it looks pretty interesting as well, especially since this CPU requirements are much lower, which if I at RoboCup want to simulate something and I want to keep my tea warm, I run Gazebo and put my teacup next to the fan, and it'll stay warm for the whole day.
Okay. Yeah. Thanks for your answer. Thanks.
I have one question that's usually, well, it sometimes brings nice stories. What is the most mind-blowing issue you've come across?
Mind-blowing issue?
Anything. Software, hardware, anything you can think of.
It's a good one. Don't know any specific issue, but I have a funny anecdote that's maybe also interesting. So at one point, these RoboCup challenge, they start out with the robot just outside the apartment, just outside the front door. Robot has to say knock knock, or team member has to say knock knock, etc. And then the challenge actually starts. But we have a trigger on our robot that waits for the door to actually fully open, measure the distance to the door. If it makes a sudden jump to a couple of meters, that means door is open, let's go in. But at some point we were testing with our robots and nobody was paying attention to the robots. The emergency stop was not pressed, which is bad practice, but it happens. So we were chatting, debugging something, and somebody opened the door, went through it, shut the door again. But a robot was triggered to say, hey, I need to start this. I need to go to the other side of the door because that's where I get my command. And so apparently this happened. We didn't see that happening. And the robot, as the door was closed, the robot was going around the arena, all bumping over cables and all that kind of stuff, trying to get in through the back door, going in there. And only after like 5 minutes or something, someone pointed to us like, hey, guys, your robot is doing something, and we don't know what, but it's moving around, and maybe you should take a look at it. So that was interesting. So some sort of deadlock going on, I guess. That was pretty funny. And as but I can't don't know if any super weird issues from the top of my head that I can dig into. No. Lots of funny anecdotes though.
Yeah, that anecdote was quite funny. First thing that would come to my mind would be Skynet, probably. Yeah,
like almost robot going wild. Yeah. That was pretty funny. Yeah.
We have about 5 minutes to the end of this meeting. So if anyone else has questions, now is the best time to ask.
Hi, I guess I'll ask, how do you manage to spend any time on RoboCup given that you now have a family and a job?
That's a good one, actually, because I've been, especially since the pandemic hit, I've been a bit of, took a more laid back position on RoboCup. So we had our baby last June, and well, so university has been closed anyway. So and doing this also remote has been really bad for my motivation doing this. So I haven't been involved that much lately. But I managed to, but I do have some other projects going on, which I could spend on RoboCup as well. But instead I've been building a cabinet for my for a son. So that's, which I could have also spent on RoboCup, but I have some priorities. And when that's done, I'll get back to spending my Tuesday evenings on RoboCup. So actually, how our team works is we have. On Tuesday evening is team evening, so everybody meets at the university, has pizza, and programs robots. And then the occasional Saturday goes there as well. And I hope to have those. Now our kid is a bit older again. I really hope to have those Tuesday evenings back again. But fingers crossed, we'll see. So I haven't gotten around to actually mixing those yet.
Thank you.
Yeah, welcome.
I have a short question regarding the speech stuff. As I told you before, I've been working on receptionist and I've successfully completed the task, also like on the real hardware and in the simulation. So which speech packages have you like worked out up till now that like without using like machine learning and stuff like that, like the normal, because unfortunately I don't get an opportunity to win the RoboCup because of this pandemic. But what I've seen from the YouTube videos is there's a lot of noise from the background.
Yes.
So when you're speaking with robot. So from your experience, which packages would you suggest for a team to explore?
So we've also been searching around for this stuff a lot. So at the moment we are using Dragonfly, which runs in a Windows virtual machine on our robots. And the handy thing about this that it can use this more grammar definitions. So it really limits the amount of misinterpretations, but still it's pretty bad. It's not perfect. It's quite okay, but not as okay as I would like it. Before we've been using Pocket Sphinx, but without the grammar and language modeling features. But also having a good microphone, an aiming microphone, really helps, or directional microphone that also helps a bit. Yeah.
Okay.
For the HSR robot, that actually comes with, I think, Julius text-to-speech, which works okay if you're Japanese, apparently, if you're for Japanese language, but doesn't work as well for English in our experience. Yeah. But at the moment, we have a guy looking into machine learning type speech recognition as well, and trying to mix that with the grammar and language models as well. But yeah, since we're all remote, maybe join our team and help develop that. That would be cool.
Yeah. Thanks.
All right, if there are no more questions, I think we can wrap up, unless someone has the last one. All right, then Thanks a lot, Loy. It was super interesting, and yeah, I'll be looking forward to seeing what you do after the pandemic as a team.
Yeah, me too. Yeah, thanks everyone for joining. Was nice to present. It's been a while since I presented something for a lot of people. So thanks for joining. And yeah, if you have any more questions, you can ask them in the Slack channel or whatever. I'll try to answer them. Right, thanks.
Great. Thanks.
Awesome presentation, Loy. Thanks a lot.
Welcome.
All right. Bye, guys. See you.
Okay,
Bye-bye.
thanks.
Bye.